Hello, everyone. I am Saeed Jaharmi from the Multiverse Computing. So in this session, I'm going to talk about tensor networks and its application in deep learning. So this is the second talk from the series of two talks that I was going to deliver here on the application of tensor network in different contexts of machine learning. So for some of you who were here first meeting, if you remember, I presented some introduction, first of all, on the machine learning itself, then on tensor network and how technically tensor network can be applied to some certain classes of machine learning, such as the kernel learning for the classification tasks. So, however, today I will talk about the application of tensor networks in deep learning, especially by focusing on deep neural network. And I will tell you how we can basically use tensor networks to improve the accuracy and training of and the performance of neural networks. And the main idea of this talk is to show you that ideas which are coming from quantum physics can still be leveraged and used to improve classical algorithms, such as the algorithm used in different machine learning tasks. Today I will focus mostly on the neural network and show you that how tensor network can be integrated into the neural network to build something new, which we call tensor neural network, or TNN. Okay, so again, since there might be a couple new people in this meeting, I will give you a short and brief introduction to tensor networks so that later on I could tell you how it can be integrated into the architecture of the neural networks. So first of all, what is tensor? Well, tensor is nothing but a multidimensional array of data. So for example, if you are familiar with any programming languages, you know that there you can define matrices, multidimensional arrays, vectors, and things like that. So these are all instances of the tensor. So a vector is an example of a one-dimensional tensor, which the dimension of these tensors, we call it the rank of tensor. So a vector then is a tensor with rank 1. It has one dimension, and each dimension could have multiple elements. Okay, a matrix is an example of a two-dimensional tensor, or a rank 2 tensor, which can have two-dimension. In a graphical notation, it is represented by these square matrices. It has two dimensions represented by these two indices. A rank 3 tensor is again have three different dimensions or three indices. It can also be represented by these cubes. And a multidimensional tensor or a high order tensor technically can have n dimension, which is a generic multidimensional array. Also, a rank 0 tensor, which is a tensor with 0 dimension, is basically a single number or a scalar. So, however, to work with n-dimensional tensor or high-order tensors, these graphical notation like this square is not efficient, because after dimension 3, you run out of a spatial dimension to draw these things. That's why a new graphical representation has been invented in the tensor network community, which is called tensor network diagrams. In this notation, every tensor can be represented by an object, say a tensor, and then every dimension of this tensor is represented by a link connected to that object. So for example, a vector is a one-dimensional tensor, then it has only one single link connected to it. Matrix is a two-dimensional tensor or a rank 2 tensor. It has two links connected to it. A rank 3 tensor has three links connected to it. And a high-order tensor, basically, there is a tensor that many links is connected to that one. So these graphical notation not only help us to represent the high-order tensor, but also they can be used to represent some linear algebra operation on these tensors. For example, a vector matrix multiplication is basically represented graphically by connecting the vector and the matrix along their shared indices. So for example, a matrix vector multiplication is nothing but the sum over the shared index j here. This shared index j is basically this link which is connected between these two guys. So it means that when you have a sum over a shared index, you just connect the tensors along that link. So this operation is called tensor contraction. So I will use tensor contraction. Whenever I say contraction, it means that I am sharing on the indices represented by the connected links between tensors. This second example is the example of multiplication of two matrices. Both of them has two legs connected to them, and then there is one link which is shared between them, which is equivalent to the sum over this shared index J, which is, again, the output is also a matrix because it has two links. So actually, the number of open links in this operation actually tells you the rank of the resulting tensor. So this guy, the third example, is actually basically two tensors or two matrices which are connected along both of these legs. There is no open link, so it is like a trace over both indices, and then the outcome would be a single number because there is no link connected to these two guys, no open links. Okay, now a high order tensor or an index tensor is also represented like this, which depending on the size of each individual dimension and also the number of these dimension, number of parameters in this high order tensor or an index tensor could be exponentially large, which is efficient. After some while, you will run out of memory and computational resources to work with these n-index tensors. However, tensor networks come into play, shine here, and it provides you with tools to factorize this big tensor and represent it in terms of the contraction of or the product of these smaller tensors. So these smaller tensors have much fewer parameters, and the total number of parameters in this network can be hugely or substantially larger than the original one. And this reduction in the number of parameters can have a lot of advantage. Of course, this tensor factorization is not unique. It could be represented in many different factorized ways. However, I will give you first some properties of these factorized tensors. First of all, when you represent a very big tensor in terms of a smaller tensor network, you gain exponential reduction in the memory. It means that you need less parameters, so you need less memory to store these tensors in the computational resource. Of course, when you have fewer parameters, it means that you can do computational operation like addition or product on these tensors in an exponentially faster speed. On top of that, some of these tensor networks actually have some physical insight that describes some quantum system and some physical system in condensed matter physics. Like, for example, this specific one, which you see here, it is called matrix product state. So this is one of the famous one-dimensional tensor network, which is also used in a famous algorithm in physics, which is called DMRG, which is for useful for simulation of a quantum system. This tensor network is also something that can also be used in neural network. On top of this physical insight that it provides for us, we could also build a new training and optimization algorithm on top of these tensor networks. So there are a lot of advantages that these tensor networks can bring for us. So these tensor networks, they are not only well known in physics or quantum community, they are also well known in applied maths community. There in applied maths, MPS is also called tensor terrain. So this is also known in another community, sometimes in computer science and applied math science, they call it tensor trace. Okay, so now let's see what is the advantage coming from. So again, consider this high order tensor, which has n links and or n dimension, and the size of each dimension is d. So the total number of parameters in this high n order tensor scales as d to the power n, which increases exponentially with the number of dimensions. So after a while, you will run out of memory and resource to store the number of parameters in memory. However, the corresponding tensor network, say MPS, it has the same number of dimension with size d. However, there is another dimension come into place, which we call it the bond dimension or sometimes virtual dimension. Okay, and the total number of parameters in the tensor network representation scales as n times d times chi squared, which is polynomial in n, d, and chi squared. If you are able to find a modest and a small chi, such that the contraction of this network provide a good approximation to the original one, then it means that you have a massive compression working with the tensor network representation of the original tensor. So fortunately, in many of the applications in classical physics, or also in classical algorithm like machine learning, you could find very small chi parameters that represent the original tensor. And this is actually the advantage that help us to reduce the number of parameters like in machine learning models. Okay, so on top of that, similar to the original high order tensors, you could also do mathematical operation with the tensor network, like you could sum tensor networks. The outcome is also another tensor network. This is basically the case for MPS. You could also multiply tensor network or multiply MPSs, and the multiplication is basically the generalization of matrix multiplication to higher dimension. The outcome is also, again, another MPS. So tensor networks are not only limited to the MPS, which is the tensor network for one-dimensional system. There are also higher dimensional tensor networks, which are called PEPs, which is basically the projected entangled peristate in the physics and quantum science community. There are also some other family of hierarchical tensor network, which MERA or tree tensor network are example of those things. These tensor networks can also represent for simulating quantum system in 1D and 2D. On top of that, again, once again, in applied mathematical community, tensor network or MPS is also widely used in the name of tensor chain. So in the applied math, tensor chains are basically tools to generalize linear algebra to exponentially high dimensional space. So basically, tensor network and tensor operation are nothing but linear algebra and higher dimensional space. With this brief introduction on tensor network, now let me continue on its application in machine learning. First of all, let's see where tensors appear in machine learning algorithms. Okay, so the very first place is the structure of data. So, for example, RGB colored images, RGB 2D colored images like these images, they usually have a 2 dimension for the height and width of this image, and also they have 3 layers for the blue, green, and red channels. So all of these information for every single pixel in the height and width and the channel can be stored as a rank 3 tensors. One of them, one dimension for the X coordinate, one dimension for the Y coordinate, and another dimension for the RGB channel. So basically, these RGB colored are basically nothing but rank 3 or order 3 tensors. On top of that, there are also some other type of data, like medical data of patients that you could have for every single patient. You could have some parameters like age, height, weight, symptoms, and things like that, that these information can also be stored in higher order tensors. So then it means that on top of the machine learning model itself, the input data can also be represented in the tensor net, in the tensor form. Now, let's see where tensors appear in machine learning as well. So in machine learning model, like in neural network, we have these this is a schematic representation of a neural network with fully connected layers, dense layers. The weight of these neural network can also be represented with high order tensor, not just a single matrix. You know, in machine learning, we usually call them weight matrices, but these weight matrices can also be represented with high order tensor. This is actually something we are going to talk about in this talk. On top of that, in other type of machine learning models, like in the discriminative and generative models, if you have most of these decision function can also be represented in terms of tensors. So like this is a decision function that the weight and these for kernel, especially for the kernel learning, the weight of these decision function for the learning can be represented as a high order tensor. These features can also be represented as vectors or as tensors. That's why tensor network is a natural language for representing machine learning models. So, for example, if you have a kernel learning problem with a decision function on multiple variables, so your cost function or your decision function could be a polynomial over n variables, and you would have a weight matrix or a weight tensor and multiple features. And this weight tensor is basically nothing but a high order tensor. And depending on the number of parameters, as I already showed you, this could be very inefficient. And storing this weight tensor in the memory could take a lot of memory for you. Of course, tensor network can come to our aid, and we could replace this rank and weight tensor by its corresponding tensor network, rather in 1D. It could be a MPS, or in higher dimension, depending on the problem, it could be a PEPS or other desired tensor network. So tensor network can come into your aid and basically factorize these guys, reduce the number of parameters, and then help you to have a more compact neural network. So then your decision function, W times feature, weights times features, can be represented in tensor network language diagram with a diagram like this. So these are the weight tensors here replaced with MPS, and these are the features which are your basically input data here represented as vectors. And then you have to train this guy. Training of this parameter is basically done by minimizing a cost function. However, this time, instead of the fine-tuning the parameters of a weight matrix, which amounts to your training, now you minimize the cost function over the parameters of the tensor. So instead of finding the optimal parameter for the weight tensor, for the weight matrix in the original language to train your model, now you minimize the cost function to find the optimal parameters of these weight tensors. This way, you could also do the same training in the same way as what you would do for a standard kernel learning model. However, your weights is not a matrix. Now your weights is a tensor network. So it is possible to show that the scaling of the parameters in these machine learning models is polynomial with the size of the input, the size of the training set, and the MPS bond dimension, or chi, which is substantially smaller than the exponential scaling in the original model. So this will bring a huge amount of compression for us. That the training actually scales linearly in these parameters. So this is also some examples on the original. Sorry, this is some examples on the two famous data sets. So this is the MNIST handwritten digits that this kernel learning with tensorized version has been applied to that, and they obtain 99% accuracy. These are reported in two famous papers. Also, the same algorithm has been applied to the other data set, the fashion MNIST, with multiple class. So this is a multiple classification, however, with more features in the images, and then they obtain 89% accuracy, okay, which is already close to the state of the art. So now let's see how tensor network can also be used to improve the neural networks. Okay, so we can build the deep neural network model for different purposes. But before going into the tensor network structure of these neural network, let me start by showing you a standard picture of a neural network with one single layer. This is a representation of a neural network with dense layer, which means that you have full connectivity between each layers. So this is a neural network with one hidden layer. X is your input. These blue ones are your neurons in the single hidden layer, and then you would have an output. So and these connections here basically are your weight matrix. So the output of this single layer neural network is nothing but W times X plus some bias, and also sometimes subjected to some activation function, and then it will give you the output of your neural network. So the X, or the input, is usually a vector. The weight matrix, as it's called, it is sometimes a matrix, and then the bias is also a vector. So then in tensor network diagrams, your X is a vector, a tensor with one single leg. a matrix is a two-dimensional tensor, and again, the bias is a vector. So basically, you could represent tensor network diagrams. W times it is a vector matrix multiplication, which is represented like this, and the bias is also another vector, which the outcome is basically means summing two vectors together and then applying the activation on these two vectors. Okay, now let's see how we can replace the weight matrices in the neural network with a tensor network. First of all, let's take a look at this example. Assume that your input vector has 216 element. You could reshape it to a rank 3 tensor with dimension 6. Multiplication of these three guys is the same as the number of the original vector x. Then you have again the same weight matrix with the same input size, and let's assume that the output is also the same. We could also reshape it to a rank 6 tensor like this. The size of each dimension is 6, and then we could actually do some factorization on these tensors from here and here, separate these legs, and then obtain a new tensor network, which is called matrix product state. This factorization can be done in many different ways. One of the famous standard factorization scheme is the singular value decomposition. I will talk about SVD and its properties later more. However, let's assume that we know how to do SVD. We could factorize this original matrix and then represent it with some tensor network, which we call it here MPO. This is our matrix product operator. This is also another famous example of a tensor network. You would see that this parameter chi, or this bond dimension or the virtual dimension, also appears here. And already, as I explained, you could get some compression here. If you find a modest chi, which is small enough here, you would also be able to reduce the number of parameters in this tensor network compared to the original weight matrix. Okay, how we do the SVD actually come from here to here is explained here in more details. You basically reshape, for example, let's assume we want to do one single SVD here. We reshape this P squared to PP and PP here, up and down, input and output. We join these two guys. We obtain a matrix. SVD is an operation which can be done on matrices. You do the SVD, and then the outcome of your SVD is basically three matrices, U, S, and V dagger. And then S is the matrix which is called singular value. That basically here, when you obtain this S, you could also do some truncation and reduce the number of parameters. I will go into the details of this truncation and reducing the number of parameters in future slides. Okay, now your neural network can be represented by its tensorized form, which is something like this. Instead of having a matrix, now you have a MPO network, which is the tensor network that output a rank 3 tensor for you. So in the full picture, the single layer neural network can be represented by a MPO representation, which is similar thing to this picture that you would see here. This is an example of a single layer neural network that the weights are now replaced by this green MPO tensor network. Okay. And then when you do the tensor network contraction or sum over all of these indices, you would obtain the output of your neural network, which is the YP. So this idea is not only limited to single layer neural network, but you could also apply it to multi-layer neural network. So it doesn't matter how many layers you would have, let's say 1,000, you could basically replace these 1,000 weight matrices with its corresponding pure tensor network. This way, you obtain a new tensor network model, in which its weight actually are replaced with these tensor networks. We call this neural network model a tensor neural network. This is the way that we tensorize it, and we integrate tensor network into the architecture of neural networks. Okay, now let's see how this tensorization also brings compression. So let's talk about SVD. SVD is an operation that is done on matrices. Let's assume that we have matrix M. The singular value decomposition operation actually decomposes or factorizes your original matrix and represents it as the product of three different matrices: matrix U, matrix S, and matrix V dagger. That U and U dagger or U and V, they are unitary matrices, so that U dagger U is equal to 1. And S is a diagonal matrix that has some interesting properties. So the elements of this matrix are all real, non-negative, and they are ordered from larger to lower. So they're ordered in a descending order. It means that you know which one of them is larger and which one of them is smaller. If you multiply these three matrices together, you will of the original M matrix. Okay, now since this matrix is ordered, since this singular value matrix is ordered in a descending order, usually many of the elements in this diagonal matrix are very small or very close to 0. So then you could decide to actually ignore or discard those small numbers. Of course, here 0.2 may not be so small, but let's assume that we could consider it a very small number. So here I can decide to replace it with 0 or totally eliminate the rows and columns and also the corresponding rows and columns of the U and V. So when I do the multiplication, now obtain a new matrix M2, which if I compare its norm distance from the original one, it would be a very small number. So that means that basically the error that you get by discarding some of the small singular values on this matrix is basically actually at the level of the singular value squared, which if the singular value is very close to 0, then when you square it, means that it becomes even smaller. So the error in these numbers are very actually small. So this operation is called truncation. So you could easily discard these singular values, so make the size of this U, S, V smaller, and then also make the size of the final M matrix smaller. So it means that you are doing some truncation. The larger this truncation, it means that the fewer number of parameters you keep or the larger comparison you are doing. So this is actually a very clever way of comparison, because in physics or in quantum physics, these singular values are telling you about the correlation between parameters of the system. When you are doing the SPD and deciding to only discard those smaller parameters, it means that you are only discarding the parameters which have very few correlation with each other, and they are not significant. If you discard them, nothing drastic will happen to your model. This way, you will have a very clever way to compress the number of parameters of your model. So the singular value decomposition is a very clever way of compressing your neural network. So now, when you are doing SPD, this chi parameter actually that appears here, the size of this chi is basically the size of the number of singular values that you are keeping along this direction. That's why by looking at the number of parameters along this dimension or the number of singular values, you would say that, okay, I only discard very small parameters, and in a clever and systematic way, I reduce the total number of parameters in my tensor network. So using tensor network for reducing the number of parameters is actually a very clever and systematic and good way to compress your neural network and reduce the number of parameters. Compressing a neural network actually help you to have fewer parameters. Then it means that you can train your basically neural network over the fewer parameters, which means that you could train it in a smaller amount of time. Or if you don't want to do the training, you just have a pre-trained neural network model, but you just simply want to reduce the number of parameters. If you do that, if you discard the parameters by using SPD, you just use the less significance parameters. So it means that you will not do any drastically dangerous thing to your neural network by discarding blindly some of the most important parameters in your weight tensors. Okay, so tensor network is actually a very clever way of reducing the number of parameters. Now, it also not only can cleverly reduce the number of parameters, you could also build new training algorithm based on ideas coming from quantum physics. So here I'm going to use some algorithm which is famous in physics, which is called DMRG. This algorithm is going to be used in simulating the ground state of quantum systems. Okay, So the idea is that when I want to update the parameters of these tensors during the training, I do it in pair. So basically, I can label them. The location of each one of them in each layer could be labeled by some index I. Then I can take two of them which are nearest neighbor, like Wi and Wi plus 1. I could contract them together and build a new tensor, which is called B. I call it a bond tensor. Then I obtain. Then I do the optimization to update the parameters of this bond tensor, and then do it for all of the pair tensor in my neural network. Okay. On top of this, I can also represent all of the tensors which are to the right and to the left of this bond tensor by another tensor which is called environment. These environments are actually approximating what is around these two neighboring tensors. Basically, it is for every single tensor, I could have two tensors, two environment tensor, one for the left and one for the right. And then if I replace all of the tensor with its neighbor and also with the bond tensor, my weight tensor in that single layer can be represented by 3 single tensor, which is one bond tensor, which amounts for these two neighboring MPO, and then all of the rest to the left and to the right are basically replaced by these environments. So now my original tensorized neural network is represented like this. I replace these two tensors here by its bond tensor, which is this blue one, and I represent all of the other ones with the left and the right environment. So a single layer neural network, which is going to update over these two, is represented by this guy. It is a small tensor network with only 5 tensors. If I have multiple layers and I want to update only these two tensors, I can represent all of the other layers by simply replacing with the environment and the bond tensor on the targeted layer. Okay, now let's see how we can update this. Obviously, I can use conjugate gradient. When I have this B tensor, if I obtain its gradient, I could do one single step of gradient descent and then update this one. B prime is the updated one, which is basically the old one minus some learning rate alpha times the gradient of this guy. Now, how can I calculate the gradient? I can use automatic differentiation. I could basically design this whole process in one of these machine learning languages like PyTorch or TensorFlow, which support automatic differentiation. If I do a forward move and do some mathematical operation, in the backward move, I can have access to the gradient of all of these tensors and basically all of these tensors in my network. Okay, so let's see. So this is my tensor network, now replaced with this bond tensor and the environment. My forward move is nothing but the contraction of all of these tensor network, which result in the output of the network. In the backward move, I would have the gradient of all of these tensors with respect to some loss function. So what I would do that, I would do for every pair of my MPOs, every pair of tensor, I would do a forward move, calculate the gradient. When I calculated the gradient, I update these pair tensor now should also be splitted to obtain the original weight MPOs. So I do a singular value decomposition here. This is my U tensor. This is the singular value S, and this is the V dagger, which I basically join root square of the singular value matrix to both of U and V dagger, and then I obtain the updated local weight tensor, which is these yellow ones. When I have these two guys, I can also update the environment well. So environment at site I is basically my W at site I multiplied by the environment on its left. The same thing is also hold for the right side. And when I update all of these guys, it means that I updated these two pairs. Then I can go to the next pair, which is this yellow one and the green one. This is called sweeping. I start from the left side, update in pair, go to the next pair until I reach the right side. Then I sweep back. I do this kind of iteration and do the update the parameters of these tensors, and this whole process is called DMRG sweeping update. Okay, this is something similar to what we do in physics. for simulating the ground state of a quantum system. Now let's see some examples. Okay, I can build different tensor neural network model for different machine learning tasks. First of all, let's take a look at the regression. So this is these blue ones are some random linear data, which if you look at it by eye, you would see that the distribution is basically a linear distribution. So I can fit a linear line to this distribution of points. So I built a tensor neural network model for linear regression, and this red one is the outcome of this tensor neural network after training. You would see that it fits this linear distribution in a very accurate and well-behaved way. We could also add more complexity. We might have also nonlinear regression. So here you would see that these blue lines are the random distribution of a sine function. So I also created a nonlinear neural network model and did the training. And then you would see that this red line is basically a very accurate fit to this random sine nonlinear distribution. To give you more insight, how does it work? It's basically similar to any neural network architecture that here we did the implementation, for example, in TensorFlow. So for the nonlinear regression, you would see that my neural network model has multiple layers. So it has the good thing is that it can be integrated with dense and tensor layer as well. So you would build a multi-layer neural network. So it has it has 3 tensor layers here, one dense layer as the output, and also one dense layer which is not in front of the tensor layers. This is because when you are doing tensor decomposition, there might be some size mismatch between the size of input vector and the size of the tensors in the first layer. You could also introduce some dummy dense layer which is not trainable, and then technically this is nothing but a 5-layer neural network, which some of its layer or dense layer are replaced with the tensor layer. Okay, you could easily build this tensor layer in any desired machine learning algorithm and use conjugate gradient with some sweeping algorithm or without sweeping algorithm to do the training. Okay, so this is the example of the regression. Now let's go to some classification tasks. So these are 2 examples of the classification. This is the binary classification on 2 data sets of Gaussian blobs, which is 2 separate distribution of Gaussian distributions. The open circles are actually the training data, and the filled circles are actually the test data. And you will see that the test data overlap in a very good way to the training data, and obtained accuracy 99% for this binary classification. Let's increase the complexity. This is another example of a ternary classification with 3 different classes with a spiral distribution. And this green, let's get back. This blue, red, and green are the distribution of these spirals. This blue region, the red region, and the white region are the margins of the decision, and the accuracy on classifying this distribution, we obtained 96%. Of course, these simulations were done on a simple MacBook, and it was quite accurate. We could also fine-tune the simulation to reach more accuracy, but this is just for the presentation showcase. We could easily show that with 100 sweeps, we could obtain 96% accuracy. To show you the architecture of this classifier, for the spiral distribution, you would see that it actually contains 1 single tensor layer, a dummy dense layer to compensate for the size mismatch, and a single output with 3 basically units with softmax activation to basically characterize this 3 classification. Okay, So another good interesting things about this DMRG training is that not only it gives you the power to do the training, and the training actually works very well. This is the loss function with the sweep iteration for the Gaussian blob distribution. You would see that the loss actually goes to very small value in very few steps. These are actually the size of these chi. These are the size of bond dimension. You would see that for relatively small sizes for the bond dimension of the tensor, you already get very good convergence in the algorithm. On top of that, when you do the SVD during the training, you have access to the singular values. In quantum physics, we have some quantity which we call it entanglement entropy, which is so these lambdas are the singular individual singular values. This will give you a qualitative behavior on the correlation between the parameters of models. Okay, so when you calculate this parameter, which sometimes also called von Neumann entanglement entropy, so entanglement in for quantum data, however, for classical data for machine learning, it gives you a sense of correlation between parameters of your models. So you would see that we have two Gaussian distribution, which are separate from each other. The correlation between these two distributions, as you can see, is not very high. They are actually two separate blobs. It means that they almost have zero correlation. So when you calculate the entanglement entropy, you would see that the entropy is also going to zero. When this entropy goes to zero, it is a signature of very small correlation. If it was something significant, non-zero, it would tell you that there are some correlation between the parameters of your model. So in quantum physics, when there is no correlation, we call it a product state. So it means that they are totally separate from each other. And the correlation between these two distributions are very small. So on top of the training and the learning, you would also get some physical insight from this training. All right. So here, let me summarize and conclude my talk. So, well, to give you an overview of this talk, I would say that in the era of noisy intermediate scale quantum devices, so we are still a little bit far away having a true quantum advantage. However, we could still use ideas coming from quantum physics, like quantum inspired, to improve the classical algorithm like machine learning. So, for example, tensor networks are one of the very well recognized quantum-inspired algorithm that can be used in many different contexts, like optimization and machine learning. You could, whenever you have a very big tensor or very big matrix, which is not efficient, you could replace it by its tensor network representation, or technically you could tensorize it. Not only you could reduce the number of parameters, also build a new optimization or training algorithm, new machine learning models that can actually have fewer number of parameters. This is actually very important. For example, if you want to deploy your machine learning model on a very small device like a cell phone, if you have a very big machine learning model that takes gigabytes of memory, you cannot deploy it on a small device. However, you could tensorize it, reduce the number of parameters like exponentially, massively, and reduce a model from gigabytes to, say, hundreds of megabytes, and then deploy it on a very small device, on a Raspberry Pi, on a cell phone, or on a local device that cannot be very large. So you could also basically design new training algorithm with fewer parameters. You could have training speed. You could also have significant accuracy, at least compared to the original model, with much fewer parameters. And last but not least, this tensorization is not only limited to neural network. You could also apply them to convolutional neural network, to the large language models like ChatGPT and things like that. And this is a very powerful tool that can basically brings a lot of advantage in your machine learning pipeline and machine learning tasks. So here I would like to stop and thank you for your attention and for your time.